Hey, we're going to talk about bond energy or bond enthalpy. Okay, so bond energy dissociation is the energy required to break 1 mole of bonds. So, for example, for the carbon-hydrogen bond, that is about 413 kilojoules per mole. That's the energy required. You can also define bond energy as bond energy formation, if you like. Which is the opposite of dissociation, and that would be exothermic. So yeah, it's really important to remember that forming bonds is exothermic and breaking bonds is endothermic. And if you look at a data book with bond energies, and usually they're not given a sign. So, for example, you might have you might say BR, the bond energy for that is just given as 193. It's not given a plus or a minus. Well, if you are forming the bond, it would be minus. And if you were breaking the bond, it would be positive because it would be endothermic. Plus 193, because that's endothermic. Okay, so it's important to just remember that. Also, you'll frequently see, instead of saying just bond enthalpy, it will say mean bond enthalpy or energy. Okay, and what that means is if you get a value for CH, and we said there, most data books quote it as 413 kilojoules per mole. This the actual strength of a carbon-hydrogen bond depends on the molecule. It's slightly different in every single molecule, and the value given there is a mean value. Okay, so when you do calculations to work out delta H with mean bond energies, it's not as accurate as when you use delta HF or delta HC as we've used in the past, because the delta HF, delta HC, they apply to specific compounds, where this, this is an average value over a range of different compounds. Okay, so let's do a bond energy calculation then. This is a typical one. So it's something you've probably done at GCSE. And so it's not that difficult. Let's say we've got propanone. Okay, so propanone is C3H6O, and if you burn it in oxygen, you will get carbon dioxide and water. So if we just balance that equation, so you get 3 of those, 3 waters, and that means you're going to need 4 oxygens. Okay, so we are given some bond energy values. We are given for the following. So here's the bond. So carbon oxygen double bond, and this is the value in kilojoules per mole. That's pretty strong. That's 805. We're given the CH 413. The carbon-carbon single bond is 347. OH bond in water, in this example, would be 464. And the oxygen double bond in the O2 molecule is 498. And what we were asked to find out, we want to find out delta H for this reaction, which is the combustion of propanone. So how do we go about it? The first thing to do is to draw a displayed formula, because if you don't, it's very easy to forget about a bond. So let's draw a displayed formula for the compound. So propanone these are hydrogens here. And we're going to have 4 oxygen double bonds. Right, that's going to react to give us 3 carbon dioxides, and the bonding carbon dioxide is like that, and 3 waters. Okay, so what I like to do here is some people will do this, you know, this sort of sum of the bonds broken, plus the sum of the bonds formed. I don't like doing that. I prefer to do an energy cycle. It's a bit more versatile. So what I say is, right, remember this is Hess's law. I'm going to draw Hess's law energy cycle. We always need a third thing down here, don't we? And in the past, we've had either elements in the standard state or combustion products. In this case, what we have is we're going to have gaseous atoms. So what gaseous atoms have we got here? We're going to have 3 gaseous carbons, 6 gaseous hydrogens, and no, it's not H2 because they're all separately broken every single bond. And we're going to need 9 gaseous oxygens. Again, it's not O2, these are gaseous atoms. Yeah. Right, what we're going to do is we are going to break, we're going to start off with that, we're going to break all those bonds and break it up into separate atoms. And this is obviously going to be very endothermic, this one, because you're breaking loads of bonds. And then we are going to form the bonds back together again, build them back up into the products. And this is going to be exothermic because you are forming lots of bonds. Right, there's plenty of scope for making mistakes, for going wrong here. So I would write everything out. Don't put it all in your calculator. You should make mistakes, and then also if you do make a mistake, you don't get error carried forward. So we're going to break a carbon oxygen. So that's going to be an 8O5. We're going to have to break 2 carbons. So that's 2 times 3, 4, 7. We have to break 6 carbon hydrogen bonds, so that's 6 times 4, 1, 3. And then don't forget about the oxygens. We're going to have to break 4 oxygen-oxygen double bonds, so that's that. Okay, these are all going to be positive values. These are all positive. Why are they positive? Well, because we are breaking bonds, so it's endothermic. So I'd write down there that is going to be, add all that up, you get 5,969 kilojoules. Here, well, we're going to break all these bonds. So it's going to make all these bonds, sorry. So we're going to make 6 carbon oxygen. So that's 6 times 8O5, because each carbon dioxide molecule has got 2 of those bonds, yeah. And it's going to be 6 times the OH, which is 464. Add all that up together, you get 7,614. And this is going to be negative because it is endothermic. Let's put that. I should really put it up there as well. Okay, so now what we have to do is we want to find out the delta H here. So we know that this delta H, let's do that in yellow, is equal to that, and this delta H is equal to minus 7614. So the red delta H, then we just got to add them all up together. So we do plus 569 plus 5969 and minus 7614, and that gives us minus 1,645 kilojoules per mole, and that is our answer. Okay, so just to just tell you, if you actually look up that value in the data book, I think it's not exactly that, it's about 1800. Why is our answer a little bit out? Because we've used mean bond enthalpies or bond energies. They're not specific to those compounds, they're just an average value. I think in particular, the CO bond, that varies quite a lot. I think it's bigger in carbon dioxide than it is in if you have it in molecules like propanone, aldehydes and ketones. Okay, so that is how you would do a bond energy calculation. So they're not that difficult. They're kind of GCSE, or they're just hard GCSE, really, aren't they? So quite often they'll give you they'll ask it sort of backwards. What they'll do is they'll give you this delta H value here, and they won't give you every single bond energy, and you have to work out one of the bond energies. So let's do one of those before we finish this video. So what we're going to have is we're going to have ethene. I think I'll clear this actually 1 minute. We're going to have ethene reacting with hydrogen. So it'd be an addition reaction. And that's with H2. So that's got a bond there. And that's going to form ethane. Right, now this time they tell us delta H here. They tell us the delta H for this reaction is equal to minus 100, so it should be a minus there, minus 137 kilojoules per mole, kilojoules, okay? And they give us the following data. They give us the value of the carbon-hydrogen bond, which is 413 kilojoules. They give us a value of the CC single bond, which is 347. They give the value of the H bond, which is 464. Not 464, sorry, 436. Okay, and the question is, find out the bond enthalpy of the carbon-carbon double bond. Right, how are we going to do that then? Right. Okay, just also notice this is the usual way in which bond enthalpy is given. There's no sign given here. There's no sign, it's not plus or minus, because again, when you're forming a bond, it's exothermic, so it's negative. When you break the bond, it is endothermic. That's a positive. Right, so what do we do? What's our third thing we always put down here? We put atoms in their gaseous state, don't we? As a third thing in our Hess's Law cycle. So what atoms have we got there? We're going to have 2 carbon atoms, gas, and 6 hydrogen atoms, gas. Again, it's not H2 because the gaseous atoms, we're going to break all the bonds up. So what happens is we break every single bond and we form that, gaseous atoms, and then we build them all back up again here. So let's see which bonds have we, what are we doing here. So when we go from here down to the gaseous atoms, well, we're breaking 1 carbon-carbon double bond, and we don't know what that is. So let's say, let the carbon-carbon double bond, let's call that, let's make that, let that be X. Okay, so we've got X plus 4 times 436 for those carbon-hydrogen, sorry, 413 for those carbon-hydrogen bonds. And we've also got this hydrogen-hydrogen bond here, so plus 464 for that. Sorry, 436. Add all that up together, and it comes to 2088 plus X. So that's delta H. This delta H is equal to that. And it's positive because we're breaking the bonds. Here, we're forming the bonds on this one here. So this is going to be, well, what are we doing here? We've got a 347 for the single carbon-carbon bond. And we've got 6 times 413 for the carbon-hydrogens. Add all that up together, that comes to, so that should be a minus, and that should be a minus there. Add all that up together, it comes to minus 2825. Okay. So we know red delta H is equal to the yellow delta H plus the purple delta H. And we're following the arrows in this here, so we don't change the signs, do we? Don't have to change any signs. So let's put the numbers in. So we get then, right, minus 137 is equal to the yellow delta H, so that's 2088 plus X, and the purple delta H, so that's minus 2825. So do your algebra on that, rearrange it, you get X is equal to exactly 600 kilojoules. Right, it is a positive value as well, and the way in our algebra gives it a positive value. Why is it a positive value? Because we are forming, we are breaking the CC bond here. That's what we're breaking, the bond there. So anyway, so the bond energy for this CC bond is 600 kilojoules. Right, I'm going to summarize. There's 3 Hess's Law cycles that we've done. I'm going to summarize them now, okay? We've done, okay, so get rid of that. I'm going to just use reactants and products. So we've got reactants going to products. Now, if we give them delta HC data, delta H combustion data, or they might, in a problem, they might give us not that. They might give us delta HF data, or they might give us bond enthalpies, bond energies. And we've got reactants going to products. Now, the tricky thing is, when you get one of these problems is, you have to decide what's the third thing to go in our Hess's Law triangle. Okay, now the third thing, when you're given delta HC, is you want CO2 and H2O combustion products. So which way do our arrows go? Well, you're burning the reactants and the products, so the arrows both go down. You form the CO2 from them, okay, and you work out the numbers here from the enthalpies of combustion and here, and work out your delta H value that way. If you want to work out the delta, if you want to work out the enthalpy change of the reaction, they give you delta HF data. Then what's the third thing we have here? Well, it isn't combustion products. You put elements in the standard states. And that means O2, H2, etc., not just separate atoms. So which way do the arrows go there? Well, it's enthalpy of formation. So you're forming your products and your reactants from the elements, so the arrows would go up in that case. Okay, and the numbers on those arrows is just going to be from your delta HF values, yeah. And then the final energy cycle we've got is if you've got bond energies, okay, if they give us bond energies. What's the third thing we put in our Hess's Law? Well, you put atoms in their gaseous states here. So that does mean HO, etc. It's not H2, O2 and stuff, yeah. And which way do our arrows go there? Well, the easiest thing to do is say you break all the bonds there, and then you build them up and make them again. So I'll just write down there. So you break. So what kind of values are going to be? That's going to be an endo. So we give it a positive value. And here we make. So that's going to be exothermic, and so that you give all the numbers a negative value there. So there's your 3 cycles, and that's you've got to know when to use each one. So you look at the data that you're given. What data have you been given? Have you did delta HC, use that one? If you give delta HF data, you do that one. And bond energies, you do the last one.